The internet was designed as a decentralized system. Theoretically, if Alice wants to send an email to Bob, she can set up an email client on her computer and send that email to Bob's email server on his computer. In reality, very few people run their own email servers. We all send our emails to centralized services like Gmail, and we connect to those centralized services using our own client, which is usually a browser on our laptop or a mobile application on our smartphone. Gmail is popular because nobody wants to run their own email server. It's too much work. With Gmail, our emails are centralized, but with centralization comes convenience. Similar centralization happened with online payments. If Alice wants to send $5 to Bob, she needs to go through the centralized banking infrastructure. Alice tells her bank to send $5 from her bank account to Bob's bank account. This is not how it works in the physical world. If Alice wants to pay cash to Bob, she doesn't have to go and meet him at a physical bank. She just takes out the $5 bill from her wallet and hands it to him. That's cash. The invention of Bitcoin proved that digital wallets and peer-to-peer payments are possible. But running your own wallet is like running your own email server. It's inconvenient, and so we trade decentralization for convenience once again. We use services like Coinbase, where users buy and sell cryptocurrencies in a centralized provider. There are people in the cryptocurrency community who hate the idea of Coinbase. These people keep their cryptocurrencies spread out on their hardware wallets. Some of these people probably also run their own email servers. Are these people just adding unnecessary inconvenience to their lives for no reason? No. These are smart, successful people. They don't like to waste time. So what are they doing running their own email servers? Distributed systems theory teaches the risk of a centralized computer system. If you have a single server that all of your communication has to be routed through, your computer network will stop functioning if that single server dies. Today, civilization is reliant on centralized computer systems, and this is fundamentally dangerous. The 2008 financial crisis proved how risky it is to centralize all of our money in the hands of a few people. The Equifax breach proved how risky it is to centralize our identity in the hands of a few people. What happens if Dropbox runs out of money and has to shut down? What happens if all of the data centers at Amazon Web Services get simultaneously wiped? What happens if Coinbase gets hacked and every user at Coinbase loses all of their money? We have seen centralized systems collapse. The people who are running their own email servers are not crazy. Even if Gmail disappears tomorrow, those people will still have access to their emails. And with the example of email, we see that deploying and managing a centralized system is possible. You still can deploy and run your own email server. Decentralization is a desirable feature of computer systems. So how can we make more of our applications decentralized? The cypherpunks spent decades thinking about how to make decentralized money a reality. Satoshi Nakamoto invented the blockchain, and now we have a computer science construct that enables decentralized money. The blockchain also happens to enable many other decentralized applications. By solving a specific problem, Satoshi came up with a general solution, and this is how progress often happens in computer science. In order to fix a very specific system, we create a new tool. That tool can be applied to other systems that we don't anticipate. The blockchain is a tool that solves one set of problems in a distributed system. Conflict-free replicated data types are another type of tool. Conflict-free replicated data types, or CRDTs for short, are objects that can be mutated by multiple users at the same time without creating data corruption. The most common example of a conflict-free replicated data type is the shopping cart. Let's say Alice and Bob share an account on an e-commerce website. Alice is building a house, and she wants to buy some tools online. So Alice has a shopping cart with a hammer in it. Bob logs on to the e-commerce website from a different computer at the same time that Alice is logged on. Bob just wants to buy a tuxedo. He doesn't know why Alice left a hammer in the shopping cart, and he doesn't want to buy it, so he clicks a button to remove all of the items in the shopping cart. At the exact same moment, Alice clicks from her computer to add a drill to the shopping cart. The server receives both requests. Bob wants to delete all the items in the shopping cart. Alice wants to add a drill to the shopping cart. Both requests occurred at the exact same time, but we have to decide how to process them in some order. This is a situation known as a conflict. Which request should execute first? Should the resulting shopping cart be empty? Should the shopping cart only have a drill in it? In either case, Alice or Bob is going to be disappointed. There's no way to avoid that. But we do need some way to resolve the conflict deterministically. We do not want to have to send a message to both Alice and Bob that says, "Sorry, our shopping cart cannot handle your request. Please try again later." We need the shopping cart to be a conflict-free shopping cart. And today's episode is about the different techniques that can be used for conflict resolution. The shopping cart is a simple example where user collaboration leads to conflicts. Imagine all the other ways that you collaborate with other users. Chat systems like Slack, social networks like Facebook, document systems like Google Docs. One way to resolve these types of conflicts is through a technique called operational transform. Operational transform requires that all the operations in the distributed system be funneled through a centralized server. When a conflict occurs, the centralized server detects the problem and figures out how to resolve it. Google Docs uses operational transform to resolve the frequent conflicts that occur when two users are sharing a text document. But operational transform only works if you have a centralized server. An alternative solution is conflict-free replicated data types, which maintain each user's replica of the data in a format that allows the client copies to resolve conflicts in a peer-to-peer fashion without a centralized server. Here's the last example, and we will get to my interview with Martin Kleppman eventually, but just this example. Alice and Bob are now collaborating on a document that uses a CRDT data structure under the hood. The document is represented as a conflict-free replicated data type on each of their computers. So whenever they send their local changes directly to each other, any conflicts that occur can be resolved directly on their client. They don't need a centralized server. Alice and Bob can collaborate on a document just like they might send emails to each other if they both had an email client and an email server hosted on their computer. With CRDTs, we can build decentralized collaborative applications. But CRDTs are hard to use. Just like with blockchain technology, we do not yet have the simple, elegant abstractions that let inexperienced programmers build peer-to-peer applications without the fear of conflicts. Martin Kleppman is today's guest, and he is a distributed systems researcher as well as the author of Data-Intensive Applications, which is a fantastic book. Martin is concerned by the amount of centralization in our systems today. He's concerned about the centralization of our computer networks, and he works on CRDT technology in order to make it easier for people to build peer-to-peer applications. Most of the people who know how to build systems with CRDTs are distributed systems PhDs or database experts or people working at huge internet companies. How do you make developer-friendly CRDTs? How do you allow random hackers to build peer-to-peer applications that avoid conflicts? Well, you could start by making a CRDT out of the most widely used generalizable data structure in modern application development, the JSON object. In today's episode, Martin and I talk about CRDTs, conflict resolution, and the idea of decentralized application development. This is Martin's second time on the show, and his first interview is the most popular episode of Software Engineering Daily ever. You can find a link to that episode in the show notes, or you can find it in the Software Engineering Daily app for iOS and for Android. In other podcast players, you can only access the most recent 100 episodes of Software Engineering Daily. With these apps, we're building a new way to consume content about software engineering, and you can find all of our back catalog episodes. And these apps are open sourced at github.com/softwareengineeringdaily. So you can download those apps. There's a link for the Software Engineering Daily apps in the show notes and find all 600 plus of our episodes. And these apps provide recommendations based on the episodes that you have listened to in the past. So people have had trouble finding episodes that are appealing to them. Well, these give you a recommendation system based on things that you've already heard. With that, let's get on with this episode. You are building a cloud-native application, and you need to pick a cloud service provider. Maybe you're just starting out with a new app, but you have dreams of scaling into the next giant unicorn. Maybe your business has been using on-premise servers, and you want to start moving some of your infrastructure to a secure cloud provider that you can trust. Maybe you're already in the cloud, but you want to go multi-cloud for added resilience. IBM Cloud gives you all the tools you need to build cloud-native applications. Use IBM Cloud Container Service to easily manage the deployment of your Docker containers. For serverless applications, use IBM Cloud Functions for low-cost, event-driven scalability. If you like to work with a fully managed platform as a service, IBM Cloud Foundry gives you a cloud operating system to control your distributed application. IBM Cloud is built on top of open source tools, and it integrates with all the third-party services that you need to build, deploy, and manage your application. To start building with AI, IoT, data, and mobile services today, go to softwareengineeringdaily.com/IBM and get started with countless tutorials and SDKs. You can start building apps for free and try numerous cloud services with no time restrictions. Try it out at softwareengineeringdaily.com/IBM. Thanks again to IBM for being a new sponsor. We really appreciate it. Martin Kleppman is a distributed systems researcher and the author of Data-Intensive Applications. Martin, welcome back to Software Engineering Daily.
Hi, Jeff. Thanks for having me.
You are doing some research in the area of distributed systems, and I want to start with the motivation for that research. Before this interview, we were talking about the good old days of Microsoft Word, where you would save a file on your computer, and it was actually just saved on your computer, and it was not shared with anybody, unlike the Google Docs of today, where you save something on Google Docs, and it's automatically synced with the cloud.
Yeah.
In many cases, that's a feature. Like, that's very desirable, right? If our computer gets destroyed, or if we happen to be somewhere without our laptop, we can access our file in the cloud. But under other conditions, this model might be more of a bug. Describe the conditions that you started to think about the research that you're doing today.
Well, so I think about if you create an app, create a file on your local computer with whatever software you're running locally, then you own that data for yourself. And you can share it with others if you want, but primarily it's your own, it's stored on your own machine. Whereas now we're using all of these web apps and services, which are super convenient, as you say, but now all of the data, the primary copy is stored somewhere in the cloud, maybe on Google servers, and we no longer really have that same sense of ownership of our own data. So you might be using some service run by a startup that might go bust any day, and then you would actually lose access to all of that data because you don't have a locally runnable copy of the software and you don't have a copy of the data locally. So what I'd like to get to is a place where we can have exactly the same kind of convenience and interactive collaboration that we get with these modern web apps, but at the same time, users retaining their own ownership of the data. So part of that is also wanting it to work offline because, sometimes you're on a plane and you just don't have an internet connection right now. But partly about just this sense of ownership as well, and the ability to keep the software working even if the company behind it goes bust.
Let's contrast this with a few decentralization models that people are exploring today. There was a popular episode we did a while ago about a decentralized social network called Scuttlebutt.
Mm-hmm.
So apparently some of the most prolific Node.js contributors are people who live off the grid, and they have intermittent network connections, and because one of them, for example, lives on a solar-powered sailboat that goes around the earth, and he's just, kind of explorer, likes the idea of living off the grid. Yeah. And this type of person obviously dislikes the centralization of the internet services. And I can tell you, I have my own nightmares about the centralization of internet services. AWS is kind of a single point of failure in our in our way of life today. If AWS disappeared, what the heck would we
Absolutely.
do? We talk about you talk about too big to fail for a bank. AWS is like, and no fault of AWS. Like, they built a wonderful, inventive service. It's just that's what happens sometimes.
Yeah, and I find it astonishing that, like, if you want to synchronize a file between your laptop and your mobile phone, and they might be 30 centimeters apart from each other, but actually the best way of doing that seems to be via a data center in Virginia, because AWS just has such a hold over so many apps.
Yeah, we might call that something like a code smell or infrastructure smell. There's something going on there that seems wrong.
Yeah, exactly. Or people make fun of GitHub, for example, because like Git is this nice decentralized version control system. So hey, let's put all of our repositories in a centralized service and only be able to access it through that.
Right, okay. So Scuttlebutt, the way Scuttlebutt works is something like people are doing stuff in their social network, and the nodes opportunistically share information with each other. Whenever you happen to be close enough to another node that is in the Scuttlebutt network, you share your timeline updates or your chat messages, and people who are curious about that can go to that episode. The other decentralization approaches people are exploring these days are around the blockchain. Centralized, or I'm sorry, having a decentralized transaction management system. And this can apply to blockchains that are money, in the case of Bitcoin, or compute, in the case of Ethereum, or file storage, in the case of Filecoin/IPFS. You are concerned with a slightly different challenge of our distributed systems and our data sharing. Give a little bit more color on the difference between the challenges that you're approaching and those of something like a Scuttlebutt or a Bitcoin.
Yeah, so with the case of blockchain and Bitcoins, what we have there is, as you said, a mechanism for decentralized agreement on transactions, which is a very powerful construct to have, but it's actually not what we need for typical data synchronization. So, for example, in what I said earlier is like I've got some data on my phone, I want to sync it to my laptop. Maybe I have a Bluetooth connection between the two. Maybe I'm sitting on a plane and I'm not actually connected to the internet, but I still want to be able to sync data between those two devices. That's a completely reasonable thing to want to do. And for that, I don't need a blockchain, because they're connecting to some kind of blockchain network and getting a transaction registered and waiting for the block to be approved would be complete overkill. All I want to do is sync some data between some devices. So I think blockchains are solving an important problem, but it's a very different one from this kind of data synchronization and offline working that I want to support. And then with Scuttlebutt, I don't know very much about the technical internals of how it works, but it sounds to me like it's mostly about, like, one person can post a message or write an update of some sort, and that gets synced to other people then who follow that person. And so that is great. That kind of data synchronization works really well because there's a single author of the message or of the update, and then the system just needs to figure out who needs to receive a copy of that message. Mm-hmm. However, if you think about a Google Docs, for example, or a spreadsheet, in that case, you've actually got this shared data structure that several people can edit at the same time. And so that's a bit different then from just posting an update, because the update has a single author, whereas a Google Doc may have multiple authors and they may be changing things independently of each other in different places on different devices. And so there we still need to make sure that we end up with a consistent document at the end.
The area of computer science that we could label this problem might be conflict resolution.
Yes.
Two people collaborating on a document or collaborating on anything. Like a document, I've got hello world, you delete the word world while I am adding my name is Jeff to the document. Should the document then say hello world, my name is Jeff, or should it say hello, my name is Jeff? You could make arguments in either direction, and we'll certainly get into that. I want to work our way slowly towards the discussion of resolving that kind of conflict, the conflict in a distributed document, with maybe some easier examples for people who are less familiar with distributed systems to understand. Why don't you give a simple example of a conflict that can emerge in a distributed system and the way that we might resolve it?
So a classic example that's often used is an Amazon shopping cart. That was the case there was that you have maybe different computers making updates to a cart, like adding stuff to a cart or removing things or changing the quantity of items. And potentially those updates can go to different servers, different database servers. And so you can end up with actually different servers having different versions of the cart. So on one, the product A has been added, on a different one, B has been added. And so now after the connection is restored between those, you want to get everyone into the same state. And probably that would be a case where both A and B have been added. So this is an interesting example that's often cited because you would think that the easiest way of solving this is just to take the union of whatever you have on the different copies. So that is, if one server has A in the cart, if another server has B in the cart, then the result is that you should have A and B when you merge them together. However, the tricky bit with this is if you also want to support removing things from the cart. And so it could be then that actually the starting point was that you had A in the cart, and then you came along and wanted to remove A and instead add B. And now, if you just do this union to merge together the different copies, then actually you make the A item reappear in the cart, even though the user actually wanted to delete it. And so that's where these data structures start becoming more difficult. If you want to support things like deletion, or if the data structures are more complicated than just like a set of items, but you want to maintain the order, or you want to do text editing, you want to have some kind of tree-like data structures, all those things start becoming trickier.
Today's sponsor is Datadog, a monitoring and analytics platform for cloud-scale infrastructure and applications. Datadog integrates seamlessly with more than 200 technologies, so you can track every layer of your complex microservice architecture all in one place. Distributed tracing and APM provide end-to-end visibility into requests wherever they go across hosts, containers, and service boundaries. With rich dashboards, algorithmic alerts, and collaboration tools, Datadog provides your team with the tools that they need to quickly troubleshoot and optimize modern applications. See for yourself. Start a 14-day free trial today, and Datadog will send you a free t-shirt. Go to softwareengineeringdaily.com/Datadog and get your free soft t-shirt. Thanks for listening, and thanks to Datadog for being a sponsor. And let's get back to the show. At a fundamental level, if two transactions occur at the same time, and then they both hit the server, and the server decides on some ordering of those transactions, the ordering of those transactions is going to lead to what the end result of that conflict resolution becomes. Does that just lead to a situation where the server is essentially making a subjective decision, and we have to put rules in place around how a conflict is resolved? Or can we reach some objective truth about how a conflict should be resolved?
Well, so the classic way of doing this in databases is with serializable transactions. And so that is, in that case, you do really have the database putting an ordering on these things. And for example, you may know that first A was added to the cart, then A was removed from the cart, then B was added to the cart. And so it's very clear that adding A happened first, then removing A happened second. So therefore the end result should be that A is removed. And so it doesn't then start reappearing again. So serializable transactions are great if you can afford them. But once people started to scale these systems into larger and larger things, potentially even with geographic replication, you run into the problem that you now have to send all of the updates to a central server, or you need some kind of leader or master database, which actually decides on that ordering. And that, unfortunately, runs counter to wanting very high availability. So if you want to be able to have the system continue working even when bits of the network are disconnected from each other, you have a network partition, then you actually want different servers to be able to independently accept writes. And now, in this case, you've got two different servers, and the ordering of the writes that happen on those two servers is no longer clear. And so what we're dealing with here now is a kind of divergence between these two. And we can define what constitutes a valid merge once the two come back together again. But sometimes it's not entirely obvious, like what a correct merge would look like.
This has been a problem in computer science since the 80s, since I think the late 80s when people started talking about this seriously, maybe even earlier. Is this a solved problem, or give a history of the evolution of attempts to solve this conflict resolution problem set?
There's a surprising amount of drama, actually. You wouldn't believe it, but people have been looking at this for a long time. I mean, the part of this is like the sort of cap theorem way of thinking, which actually goes back to the 70s as well, where people realized, like, oh, we have copies of this data on different nodes. They might both get updated. Now we have conflicts that we need to resolve. And the initial versions started out just very simple with maybe version numbers and getting the user to write their own code to merge versions together. But like we saw in the Amazon shopping cart example, it's not always actually that simple to do that merge correctly. Now, there's one line of research in this area called operational transformation, which does go back to the 80s, where people studied mostly the problem of collaborative text editing. So that's like what you get with Google Docs, where you've got several people contributing to some text document. And what you want to do there is that each user has a local copy of the document on their own computer. Nowadays, it's in our web browser. And whenever you type a letter, you want to make that change immediately to your local copy. So you don't want to have to wait for a network round trip before the letter you type appears on the screen. So you apply the changes locally immediately, but that means then asynchronously, some later point, that change gets applied to other people's copies of the document on other computers. And now, during that little period of time, after you apply a change locally and before it gets sent over the network, you can get divergence. So the document can drift apart slightly. Different users' views of the document can drift apart slightly. It's even more extreme if you want to support offline editing. So if you allow people to change the document offline, then they might have a whole bunch of changes made on one computer and a whole bunch of changes made independently on a different computer without knowing about each other. And then at some later point, they both come back online and they resynchronize. So I said, operational transformation has been studied for a long time, and there were a whole bunch of algorithms that have been proposed precisely for this problem of text editing. And the problem with most of these algorithms is that they later turned out to be wrong. It's actually turned out to be an incredibly subtle problem, even just a simple problem of text editing, where the only thing we allow is inserting a letter at some place in the text or deleting a letter. Those are the only two operations. And nevertheless, some researchers would come along, propose an algorithm, and then 2 years later, some other researchers realize, oh, there are actually some cases in which this algorithm fails to converge. So there's simply some cases in which you can construct an order of operations such that at the end they don't have the same document. It doesn't become consistent. It remains permanently inconsistent. So the researchers propose a different algorithm that solves this bug. And then 2 years later, some other people find yet another problem. Again, there's some circumstances in which they fail to converge. And if you go through the literature on operational transformation, there are I think 5 failed algorithms that have all been published in good academic venues. They've all had peer review, and nevertheless, they're simply wrong. And so a couple of operational transformation algorithms have survived this disaster. And Google Docs is now actually using one of the remaining ones that actually turned out to be correct. But it does so at the cost of sending all of the changes via a central server. So some of the operational transformation algorithms tried to support these kind of decentralized architectures where you could do peer-to-peer synchronization of data. And almost all of the peer-to-peer operational transformation algorithms just went wrong. So the problem becomes a whole lot easier if you assume a central server, and that's what Google has done with Google Docs. So that's okay, it works, but it does mean that you can't have 2 people editing while they're disconnected from the internet, for example, and just synchronizing via a network. That won't work because the fundamental assumption of the algorithm using Google Docs is that you can send everything via the central server that is hosted by Google. So then people started investigating a new family of algorithms called CRDTs. This stands for conflict-free replicated data types. And that was really like an allergic reaction to operational transformation, basically saying the entire history of operational transformation research has just been such a train wreck. We're just going to start afresh with a completely different model. And so people have proposed a number of CRDTs for text editing, but then also for other kinds of data structures like maps and sets and JSON. And that has been a whole lot more successful. So there hasn't been this kind of catastrophic failure of algorithms with CRDTs as there was previously with operational transformation. However, with CRDTs, the challenge has been more on the performance side, that some of these algorithms too slow or require too much metadata overhead, they're not practical yet. And so this is actually the area in which I've been working, in particular trying to understand CRDTs better, check that they really do work correctly, and improve their efficiency so that we can actually start building applications based on them.
Just to give people some gravity for this problem set, the shared document problem is almost a base case of problems. Because if you can imagine, if we want this ability to have decentralized file collaboration, we would not only want to collaborate on, say, a Google Doc where, it's not, or I shouldn't even say Google Doc, because obviously this would not be a Google Doc, a document. We would not only want to collaborate on a document where, if somebody, if we have a conflict and the conflict resolution uses an operational transform algorithm that results in a misspelled name or a typo or some grammatical error, it might seem like, okay, it's not a big deal. Like, okay, this works 99 times out of 100. We just end up with a typo sometimes. It's not a big sacrifice to make. Let's just use the operational transform algorithm and get our decentralized world, and that's fantastic. But if you started to collaborate on something like a blueprint for a building, right, and you wanted to have a decentralized, way of collaborating on blueprints, if that kind of thing gets a typo, that could result in like the building falls down. So that's a serious issue. And so I just say that to motivate our discussion a little bit further, and we'll get into the CRDTs in a second. But as far as the operational transform and really this whole field, I've done some shows about the Paxos algorithm, and which is really about reaching consensus in a distributed system. I actually had the privilege to interview Leslie Lamport several years ago, and it was incredible. But why isn't this a subset of the problem of consensus? This seems like a distributed consensus algorithm. We just need to come to a consensus on what the reality is. And I thought Paxos did that.
Yes, it does seem like they should be very similar, but actually they are different at a very fundamental level. So the type of consensus that you get from something like Paxos is as follows. You can have one or more nodes propose a value, and then one of those values gets decided. So the expected outcome of the consensus is that everyone decides on the same value. This applies, by the way, to blockchains as well. So there the consensus is about what is the next block going to be. And so in particular, what transactions appear in that block. And so the consensus there is about did a particular transaction happen or not. And this is actually not what you want in the case of document editing, because if you apply consensus to document editing, it would be like, I have a bunch of changes to document, you have a bunch of changes to the document. One of the two of us is going to get their changes selected, and the other one is going to be thrown away. Which is what you want in case of transactions. Like, you want money that can only be spent once. You don't want conflicts of money getting spent twice. But in the case of document editing, consensus is really not what you want, because it would mean that only one of our changes get through and the others all get thrown away. So what we want to do is we want to get into the same state. We want to reach a consistent state, but we want states to actually reflect all of the changes that have happened, and we want those to be merged together in some sensible way.
Of course.
And that is what CRDTs give us.
Right. So this is like, I make a Git branch, and I need to eventually merge that back into master, and the result of that merger is going to be a completely new thing. We are coming to a consensus, but it's a consensus that is the unification of our two disparate views on reality, rather than the Paxos model, which comes to a consensus on just one of the two perhaps disjoint sets of reality.
Yeah, that's right. And so actually, Git branches and merges is a really good way of thinking about this. A lot of the history tracking we do in CRDTs actually looks very similar to what happens in Git. And so the main thing we're trying to automate there is this merge process. And that is, you know what it's like to resolve a merge conflict if two people have edited the same code. It gets pretty tricky. And so most users, in most cases, won't want to have to deal with something that looks like a Git merge conflict. It's much easier to just merge the changes together automatically. And in most cases, people are editing different parts of the document, and so that's perfectly fine. So the tricky cases only happen if people are like literally editing the same words in the same sentence. And in that case, well, actually what Google Docs does is it just picks some resolution in which the insertions and the deletions have happened. The result might not actually be a grammatically correct English sentence, and it doesn't even try to be clever about English grammar. So the best it can do there really is just ensure everyone ends up in the same state, and the spell checker will then tell you if some of the merge conflict has produced some weird words that are not actually English. And so that is kind of the level we're working at as well, that we can't fundamentally understand the English language structure of the text. Trying to do so would just lead down a very complicated natural language processing problem, so we'd rather not even try to solve that. But just get everybody into the same state and maybe highlight if people made changes very close to each other, just to then double check that the merged result is actually sensible and meaningful.
We've laid the foundation for a conversation about CRDTs. Multiple users are changing a replicated document. Those changes can result in conflicts, whether it's talking about conflicts in a Git situation where we need to merge those, or conflicts in a text document where you have made changes to the document that conflict with the changes to my document. So we should try to represent this document in a format where conflicts can be resolved. So we use conflict-free replicated data types. What is a conflict-free replicated data type?
Essentially, it's a way of giving you a data structure that you can work with and that you can modify in certain ways, such that when several people change that data structure concurrently, the results can be merged automatically. And so, like, one data structure that you can work with, if it's a text document, is a list. So a text document we would represent as a list of individual characters. And you can modify this text document by inserting characters in certain places or deleting characters. And that is kind of enough to represent plain text already. If you have a more complex type document, say a spreadsheet, or like the architectural drawing of a building, like you were saying earlier, that would then be some larger data structure. So in the case of a CAD program for drawing, I think that would probably be some kind of tree of objects. That's typically the way vector graphics works, that you have some kind of tree of graphical objects that can be grouped together. So related things are grouped together into a subtree. And then you could potentially have people working on different parts of this tree. Like one person is adjusting the shape of the windows while another person is working on the water pipes that come into the building. And those two things can probably be edited independently from each other and can be merged together without too much trouble. So whereas Git works purely on files that it doesn't interpret, it just treats a file as a sequence of bytes, and for merging it treats it as a series of lines, and you can just do like line level merges. But with CRDTs, we tried it to more application meaningful data structures. So some of the work we've done is on JSON. So a lot of data can be represented as JSON, essentially. JSON is actually a fairly simple format. You can imagine it as a tree, and as you know, there are two constructs of JSON. There's the curly braces, which gives you a map, like a key value mapping, and there's the square brackets, which gives you a list construct. And you can nest those two things inside each other arbitrarily. So you can have like a list of maps, or a map where the values are lists, or various combinations of those things. So by expressing data at the level of a data structure, then we can define sensible merging rules. So like, for example, if we both edit a map, if you insert key A with value A into a map, and I insert key B with value B into a map, then we can merge those two quite nicely. In fact, this looks very much like the shopping cart we talked about earlier. With a list, if you insert something, I insert something, we can merge the two so that both of our insertions are preserved, and so on.
What are some of the benefits of the CRDT approach relative to the operational transform approach?
The main one really is that the algorithms work without us, assuming the central server. So as I said previously, people have tried to make operational transformation algorithms that work in a peer-to-peer setting without going via a central server, but most of them failed. So CRDTs are really a fresh start that allow this kind of data synchronization without assuming anything about the network topology. So without assuming a particular server, you can go serverless, literally serverless in the sense of actually not having any servers, because you can synchronize data via a local Bluetooth connection or via a local Wi-Fi. It doesn't have to necessarily go through some kind of central node.
G2I is a talent platform built for engineers by engineers. React Native, React, and mobile. The developers on G2I have expertise in the best tools to build your applications. When I need engineers to help me out with my apps, G2I is the first place I go, especially when I'm building with React or React Native. Contract a G2I developer to help you on a short-term basis, or hire a G2I developer full-time. And if you're looking to build cross-platform applications in React Native, definitely check out G2I. The G2I platform is a community of React Native, React, and mobile developers, and these engineers can become part of your team. If you're looking for developers to build your product, check out g2i.co. That's the letter G, the number 2, i.co. You can also send me an email, and I'll be happy to tell you more about my experience with G2I. Find your React Native, React, and mobile talent by going to g2i.co. And thanks to G2I for helping me ship my products, and thanks for becoming a sponsor of Software Engineering Daily. Is there any, what's the sacrifice there? So like, in the contrast with the Google Docs approach, where Google centralizes all the changes, that funnels them through a central server. They must, I mean, do they end up with fewer typos that way, or I mean, there must be some, I assume there's some matter of correct or implied correctness that they get out of that centralized server approach.
So in terms of the conflict resolution, I believe what Google Docs does is pretty much the same as what the CRDTs do. So in terms of like the consistency of the outcome, like if two people correct the same spelling mistake at the same time, for example, you will get the same kind of weird outcome in both Google Docs and CRDTs. One example that I like testing is what happens if one user deletes an entire paragraph and another user simultaneously changes one word inside that paragraph. And I think what Google Docs does in this case is actually the end result is a document where that paragraph is missing, except for that one word that was added to the middle of the paragraph is still there, even though that the surrounding paragraph was deleted. And this is a bit weird, but a lot of people seem to use Google Docs and manage just fine. So my thinking there is CRDTs will manage just fine as well. So the trade-off there mainly is actually around efficiency. That with the CRDTs, that at least the first generation CRDTs that were developed for this, they require a lot of extra metadata. So the document where you have like every single character is an editable item, a character you can represent in 1 byte, but you might then suddenly need 20 bytes of extra overhead of metadata attached to every character, and now suddenly your document has grown 20x in size. So that is really the trade-off there, that the operational transformation algorithms have been a lot more efficient. And what I'm working on right now in my research is how far can we push down that metadata overhead with CRDTs, so that we can make them really efficient enough to be of practical use without that 20x overhead. So in my latest experiments, I actually got it down to about 1.7 bytes overhead per character in a text document. Which,
well, that sounds great.
That is doing a lot better than like the 20x or 100x we were seeing previously.
Tell me if I have the analogy right. So with GitHub, you get basically the commit history of your entire project. I'm sorry, I think I said GitHub. With Git, you get the entire history of your project. And at any given time, I can roll back to a certain situation in that document's history. Mm-hmm. And you're talking about creating basically a document model for basically kind of any document that, if I understand correctly, the metadata, what you're calling the metadata, is essentially like a commit history, so that that any like disparate set of documents have enough historical data that they can resolve the conflicts that they might have. Is that a correct analogy?
Yeah, it's very much like a Git repository actually. And in fact, so I've been working on a implementation that we call auto-merge, which is a JavaScript implementation of CRDTs. And it works very much like that. Actually, it does, in fact, keep the entire edit history. So every single letter that was added or removed to a document, it stores that, and it just puts it in a compact representation so that you can actually look at the document at past moments in time and do this kind of time travel through different versions of the document and see who made what edit at what time.
And how do you decide when to throw away old versions of a document? Do you just keep the entire thing, or what's your approach?
At the moment, we're just keeping the entire thing, which is, by the way, what Git does as well. So with a Git repository, if you clone it, unless you do a shallow clone, you actually get the full commit history of all changes ever made. Well, and that actually seems to work surprisingly well, even for large projects. So right now, I'm working on the basis that we'll just try to keep all changes as long as we can, and just represent that in a compact way so that it doesn't cost us too much extra storage to keep all of that history. There's really just one case where you'd want to deliberately throw away history, and that is if I send a document to somebody else and I don't want that new person, that new collaborator, to see the entire editing history, because maybe there was some embarrassing stuff that I had in a past version of the document that was then deleted. And so in that case, I don't want to actually share the full editing history with someone. I just want to give them like a snapshot of the latest version. And so for that, at the moment, what we can just do is like copy it all into a fresh document and start afresh. There's probably some better things we can do around creating a snapshot that gives you the current state without the full editing history, but which still remains compatible, so that when somebody then edits this snapshotted version, you can still combine those edits with the version that has the full history. So there's some more research to be done at the moment there. For now, except for this privacy case, I think it's actually okay to just keep the full history, because certainly for stuff that is edited by humans, there's only so much that a human can type. Computers can store a lot more data than what we can type.
The blockchains that I've explored on this show often use a Merkle tree to do, I guess it's kind of like a form of compression, of compressing a history of changes that have occurred. Do you use a Merkle tree type of structure for the CRDTs?
Not at the moment, though there are some implementations that use some of these Merkle tree-like ideas. So at the moment, for our purposes, in auto-merge, the type of document we're talking about is like something like a Word document or a spreadsheet or something like that, which is fairly small. Like the total amount of data is small enough that you can fit it in memory on one computer. So for that, you don't really need these Merkle tree-like structures, because if you want to give somebody a copy of the document, you just give them a copy of the entire thing, and that's fine. So it's like deliberately small data, not big data. You could definitely imagine wanting to generalize this to much larger data structures. Like, I imagine, say, could we build something like a Facebook that is actually built upon CRDTs? In that case, you certainly wouldn't be able to download the entire social network data to every computer, so then you would have to download subsets of it. And in those cases, then techniques like Merkle trees would become relevant.
So could we go through a simple example of a conflict that could occur between two instances of a document, and how that conflict is resolved at the data structure level, how that data structure would be represented, and what would go on in the resolution algorithm?
Sure. This would be easier.
I know
with
it's
a
hard
whiteboard,
to describe over voice. I know. I will certainly put things in the show notes that people can explore. So you don't need to go into gratuitous detail that would be impossible for people to visualize.
Yeah. So I have some slides which give some examples of this, which we can put in the show notes. But I'll describe it in words. So one interesting case is you have a text document, and you have two people who are both adding text at the end of the document. So right at the end of the document, you put the cursor there, and I type one paragraph and you type another paragraph. And so what we expect at this is that the final merged result has both of our paragraphs, and it's either your paragraph first, then mine, or mine first, then yours. It doesn't really matter in which order they occur, because there's nothing really that determines what the right ordering should be, but we expect them both to be there. So this is actually an interesting case, because some of the CRDTs don't handle this particular situation very well. So some of the CRDTs I've looked at will actually take the individual letters from both of our paragraphs and interleave them, potentially. So you would end up with a jumbled mixture of letters, some of the letters coming from my paragraph, some from yours, but the end result would not be readable text. It would be some kind of mad jumble of the individual letters, which is not really a good outcome in this conflict resolution. But the algorithm that we've been working with doesn't have this problem. So the algorithm we have puts either one paragraph first and then the other one after that, but it doesn't intermingle the two. And so the way this works is you can imagine that if each letter in the document a unique identifier, and that identifier consists of a number and a node ID. So the node ID is like some kind of identifier that is the copy of the document in my browser, and in your browser you would have a different identifier. And so this just serves to make them unique. And so we can now create unique IDs for each character by incrementing the counter, the number part. Every time I type a letter, I just give it a number that's one greater than what we've had previously, and I'll attach my node ID to that. And you can do the same. So we might end up generating identifiers that have the same number, but they would differ in the node ID part, and so they're still unique overall. And now what we can do is we can actually use those numbers and node IDs to determine the final ordering of things in the document. And so the exact rules for how you do this are a bit subtle, but the basic idea is that in order to decide whether your paragraph comes first or my paragraph comes first, we actually look at those numbers and we look at the node IDs. We first look at the number. If one number is greater than the other, we put the one with the greater number first, the one with the lesser number second. So we order in descending order of those numbers, essentially. And if we end up with the same number, then we actually compare the node ID part. And again, we just put them in descending order. And so that guarantees a deterministic outcome. So no matter in which order you apply these different editing operations, at the end, everyone is going to order the insertions based on those unique identifiers, and everyone sees the ordering of those unique identifiers. And that is what guarantees that everyone actually ends up in the same state at the end.
One of the examples that I heard you give in one of your talks, I saw you give, and again, for people who are confused, that's definitely a great source of information, is the talk that I'll put in the show notes, or the multiple talks that I'll put in the show notes. But you use these examples to motivate the fact that there are not clear APIs for concurrently editable data that are not confusing. And my sense of talking to you about this is that this is actually important because there is an element of subjectivity to how we're going to resolve a synchronous change, a change that occurs at the exact same time. And the way that we resolve that is going to depend on the application. Like, we want to do different things. Maybe if conflicting changes occur when we're concurrently editing a blueprint for a building, maybe you really want to just signal the user, hey, there have been conflicting changes. Like, you want to do something about this. You want to go talk to that person physically or go give them a phone call to resolve this. You maybe don't want just like the automatic reconciliation algorithm. Is that correct?
Yeah, potentially. So there's certainly some cases where you might just want to bump it up to the user and ask the user to solve it. But it's also true that it's not always obvious if you do want to merge automatically, what is actually the right way of doing this merge. And what I'd like to get to is that we can actually have these CRDTs just available as a library that anyone can build applications off of. And you shouldn't have to have a PhD in distributed systems to make sense of those. So we really need to figure out like a programmer-friendly, developer-friendly way of expressing these data structures. And that is tricky because, like, fundamentally, if different people can change stuff at the same time, sometimes really weird things happen. And so we kind of need to translate these really weird things that can happen somehow into a set of APIs that will actually make sense to people. And I think we're gradually getting better there. So with this auto-merge JavaScript implementation that I described, I actually did a collaboration with a few folks who were building an actual example app on top of it. And that was great for learning about like what assumptions are the app developers making about how these APIs work, what kind of things do they get confused about, how can we make it better, how can we just design the API in such a way that it seems obvious and nobody gets too confused by it, even though what's going on underneath might actually be quite sophisticated. And for that, it's been really useful actually collaborating with people who are not CRDT experts, but just want to build an app and who don't care about the details of what happens internally.
So with other data structures like a map, for example, we've developed vocabulary for doing things with a map. Put and get and delete operations. Are you starting to get a sense for what the vocabulary for a CRDT is going to be?
Yes, so ideally I would like it to look exactly like your familiar data structures, like As you say, with a hash map, you can put, you can get, you can delete, and that's nice. So let's take an example of a case that I wrangled with, which I'm still not entirely sure actually what the right result looks like. You can use a map to represent, say, an item in a to-do list. So a to-do list is like a list of items, and each item will have a title that's like the text of buy milk or water the plants, and then maybe a boolean which indicates whether it's been checked off the list or not. Maybe it'll have a timestamp or a deadline or various other stuff attached to it. So we initially designed a JSON CT algorithm, and it had this weird property that if one user deletes an item from a to-do list, and another user at the same time updates the checkmark, the Boolean flag of whether it's done or not, then the merged outcome would be that you have this item in a to-do list which consists only of the Boolean field, but where the title has disappeared. And so this is really weird, because nobody really expects an item in a to-do list without the text of what that item is. So in that case, really what we probably want is that the deletion takes precedence. So if the one item was deleted from the to-do list and somebody simultaneously updated that item, we're just going to forget about that update because the item was deleted, so we don't care about the fact that it was changed anymore. It's just gone by that point, unless somebody does an undo. So that's kind of one example of where we ran into an issue. So now it seems like a reasonable way of handling this is to just let the deletion take precedence. But another case happens where you have, say, different people creating a map at the same time. So let's take as an example, say you wanted to implement Slack, your own version of Slack, and a message in Slack is again an object, and it has like the text of the message, and it has a field indicating who wrote the message, and maybe it has a timestamp. And then Slack added this ability to add emoji reactions to messages. I don't know if you're familiar with that. You can have like a...
Oh, yeah, I use that on an hourly basis.
Great, yeah. So this makes a nice distributed systems example, emoji. So you have 5 people who added the like smile emoji reaction to a message, and 3 people who added the celebration emoji, and a couple of others, whatever. So we can again represent that as a map. So let's have the top level, we have our message object, which has a key which is text, a key which is timestamp, a key which is author, and a key which is reactions. And under reactions, we have a nested map, and that map is like smiley :5, celebration :3, star :15, whatever. And so that way we're packing all of the reactions together into one object. Now, that is okay, but imagine what happens if you go back in time to the day before Slack actually had this feature of the emoji reactions. So in that case, that reactions field doesn't exist. And so now the first time somebody adds a reaction to a message, it's first got to initialize that reactions field and put like an empty object, an empty map there, and then fill that map with the first reaction. Now, what happens if 2 people simultaneously decide to add the first reaction to a message? So now you've got 2 people independently assigning a new empty object to this reactions field. What do you expect to happen in that case?
Yes.
Do you want to merge those 2 objects together? Or do you just want to say, well, these are 2 independently created maps. We're just going to keep them separate. One of the 2 is going to win, the other one is going to be overwritten. That's really tricky, because if you start going down the case where, okay, we're going to merge these maps together, then you end up going towards this problem that I went to earlier with the to-do list item that has a Boolean but not the title. But if you say we're not going to merge these 2 maps together, we're just going to keep them separate, then in some cases you're going to actually lose data. In this case, like if 2 people create that first emoji reaction simultaneously, only one of them is actually going to be preserved in the final data. And so that is the kind of irritating things that we've been grappling with. And I don't know, maybe I'm overthinking it. For now, we've just got like a simple solution that seems to work well enough. And I guess we'll have to just people will have to start building apps on top of these types of data structures and we'll just see what sort of issues and bugs people run into. But it's certainly, you run into all these kind of interesting scenarios that just don't happen when you're just writing code on a single machine. Like this whole issue of different people concurrently creating the first reaction, like in a single-threaded case, that just doesn't happen. And we're used to thinking very sequentially about the way we write our software. So, like, suddenly if you're allowing this collaborative editing, you're moving into the space where concurrent changes happen, and concurrency is always been hard for people to reason about.
All right, well, you've been very generous with your time. I want to wrap up with just a question of bringing this to market. You are doing research on this, and you're a very public research figure, so I'm sure the words that you say eventually they probably make their way into industry very quickly on a natural basis. But do you have any vision for how, this JSON CRDT, so, the world is moving towards JavaScript, obviously. JavaScript's eating the world, and JSON is eating the world in terms of data representation. Do you have a vision for how your conflict-free replicated JSON data type might make it to market and start to make it into an application like Slack?
Yeah, totally. So, as I said, we're working on this JavaScript implementation called AutoMerge, which it's by no means production ready yet, but it does work, and it's getting gradually more efficient. I've spent several rounds of iterating on the performance of it, and I think so far I've speeded it up about 3 orders of magnitude from the initial version, from which actually deduced that the initial version was extremely slow. So now it's kind of starting to get fast enough that you can actually build some reasonable applications on top of it. And so it's research code. We're using it for writing papers and doing performance measurements as well. But I am hoping that this will become good enough that people can actually use it in production for real to build real applications. So that is kind of the trajectory we're heading down there. And I believe this will matter a lot. We need not just the CRDTs, but another layer to it is figuring out the networking as well. So we've got a prototype that uses WebRTC for peer-to-peer communication between different devices, which is really neat. We can actually do surprisingly much without a server or using just the WebRTC signaling, but beyond that, just doing peer-to-peer synchronization. The downside of that is that you need people to be online at the same time in order, it's just like a video call or something like that. It only works when people are both online and can exchange edits at the same time. So I think we'll probably still want cloud services, which will then kind of act as a buffer so that I can upload my changes to the cloud, and sometime later when you come online, you can download your changes again. But, that can actually be end-to-end encrypted, for example. We don't actually need the servers to be able to read the data that's being exchanged there. It's really just using the server as a buffer of messages. And I think of this as a kind of cloud optional programming model where it's nice to use cloud services for exactly this kind of storing of data, but we also want to be able to use local networks for synchronizing data when available. So if I'm sitting on a plane, I want to be able to sync data between my phone and my laptop, even if both of them are actually not connected to the internet because I'm on a plane right now. So that is kind of the world I want to get to, where we can build applications where you can just freely synchronize data between devices using whatever networking medium happens to be available right now, where everything continues working offline. Like, seriously, sometimes offline is just really good, where we own that ourselves. So where we have a copy of the data on our local devices, where we will still have commercial apps because obviously developers have to have some business model somewhere. But if the developer goes bust, I want the software to still continue working. I want it not to have to rely on the running of some service that I don't control. And I don't want to have to deploy my own services because I don't want to act sysadmin as well. I just want stuff to be able to synchronize between my devices using the software that's running on my devices. Which is, kind of an old-fashioned way of thinking about software, but I think we'll probably come back to liking that kind of way. So that's really my vision there, that we have this control over data, that the apps work offline, they can synchronize in whatever way we like, and we have some kind of programming model for building these apps, which is simple. Because that's really, I think, the stumbling block at the moment. Like right now, you actually need a PhD in distributed systems to make this stuff work. And we need to get to a point where it's just as easy to build these kind of decentralized apps as it is to throw together a Rails web app, for example. Like building a centralized Rails web app is really simple. There are loads of Rails, there's good libraries, there's good tool support around it. What I'd like to get to is that we can do the same for these decentralized apps, that it's just as simple to throw together a simple app and it works nicely. So hopefully that's a future we can reach. It might be still another year or two, maybe 3 away, but I think we're heading in that direction.
Well, it is exciting talking to people like you and also people in the blockchain community who fully realize that the APIs are not yet there for building the Internet of Money, but they are so determined to make it work. And people are so determined to rid themselves of the burdens of centralization. And you see the failed efforts of governments, for example, to rein in that decentralization. It's fascinating to watch those failed attempts, and I imagine that industry is going to be a little bit smarter, and they're going to kind of realize, well, actually, people want this, and maybe at a certain point there'll be some inflection, and industry will start to actually think about, okay, how can we productize this, or how can we just give people what they want, and that could be a really interesting point of inflection, maybe for another show.
Yeah, right. So I spent a while, for example, talking to journalists. Journalists sometimes work with really sensitive data. If there's a whistleblower who's come to them, a source for some story, journalists are very cautious about wanting to protect the identity because they might run into trouble otherwise. And so that is actually a nice example of where you want the convenience of something like Google Docs, because journalists are working together on some article and just need to get the article ready. They need to annotate the source materials, maintain some kind of knowledge base around that stuff. But actually, it's kind of sensitive data, and so you don't want to just blindly store it in some cloud service. And so that's an example of where we see these kind of tools being like actually really important, not just a nice to have, but actually like important for people's security, that we can offer a better security model than what the web apps do today. So that's what I'm hoping will be another benefit of this decentralization as well.
All right, Martin. Well, it's been great having you on once again. I can't remember if I mentioned to you, but your previous episode is actually the most popular episode of Software Engineering Daily. And
seriously? Wow.
Yeah. It's funny. I don't know if this is a Zipfian distribution, but it's like almost 2x as popular as the second most popular episode. So it's like you are a beloved speaker. And I really appreciate you taking the time to come on the show once again. You did not disappoint. I really enjoyed talking to you. It's always very educational. So thank you so much.
Well, yeah, thank you to all the listeners. I'm always very pleased if the random rambling ideas that I talk about are actually helpful and useful to people. So hopefully it will be again the case with this one.
Are you a Java developer, a full-stack engineer, a product manager, or a data analyst? If so, maybe you'd be a good fit at TransferWise. TransferWise makes it cheaper and easier to send money to other countries. It's a simple mission, but since it's about saving people their hard-earned money, it's important. TransferWise is looking for engineers to join their team. Check out transferwise.com/jobs to see their openings. We've reported on TransferWise in past episodes, and I love the company because they make international payments more efficient. Last year, TransferWise's VP of Engineering, Harsh Sinha, came on Software Engineering Daily to discuss how TransferWise works, and it was a fascinating discussion. Every month, customers send about $1 billion in 45 currencies to 64 countries on TransferWise. And along the way, there are many engineering challenges, so there's plenty of opportunity for engineers to make their mark. TransferWise is built by self-sufficient, autonomous teams, and each team picks the problems that they want to solve. There's no micromanagement, no one telling you what to do. You can find an autonomous, challenging, rewarding job by going to transferwise.com/jobs. TransferWise has several open roles in engineering and has offices in London, New York, Tampa, Tallinn, Cherkasy, Budapest, and Singapore, among other places. Find out more at transferwise.com/jobs. Thanks to TransferWise for being a new sponsor of Software Engineering Daily, and you can check it out by going to transferwise.com/jobs.
Wow.